life example that I do bird courses. You just have to stick through it. You know, you just have to like go through all the grind. I don't know, yeah, very good. All right, no questions? Good. Or not good. All right. So last time we talked about equality constraints, which is this thick line. All right. But the real world doesn't care about that much as it cares about inequality constraints. You know, you can like have a negative cost or whatever. What's a good example? Like in the real world, you don't have to be exact. So we're actually doing useful stuff now, finally. Inequality is what you will actually see, because you can always change equality to inequality. Anyhow, right? Because if G is 0, you can approximate by like G less or equal than minus epsilon, and G, so what is it? So let me write this one, I guess. Let me write it like, what do I want to write? Yeah, whatever. I want to say something like this guy being less than epsilon. So, fine. Here are the two constraints. Minus epsilon. Yes, okay, good. Anyhow, whatever. The point is, in the real world, you can always turn equal to G being less than epsilon, and this is inequality constraint. All right? Do you understand? Yeah. So, yes. Anyhow, that's the point. So this is the real meat. You start with nonlinear constraints. First ones are equality constraints, and the second ones are inequality constraints. All right. This is Lagrange multipliers. We talked about this last week. And now we're gonna do inequality constraints. Okay, so good. What's an active constraint? So this is a nice notion that will make your life very easy. Suppose X naught is in the feasible set. We call this the feasible set. Then we call a constraint active if added it's 0. Okay, I will show you some pictures and examples. But these are the only constraints we care about when your local minimizer is exactly 0 at the boundary. Okay. If it's not, that's not the case, we call it inactive, and I will tell you why you can ignore them. So here's the picture. So can someone tell me for which constraints X star is active? Huh? And which ones are inactive? Yeah, so G1 is active, and G2, G3 are inactive. Now, why do we care about this? Let me draw a picture here. So first of all, can someone tell me what is G2 of X star from the picture? Can you guess? Is less or equal than, is strictly less than zero. Zero is over here. Here is positive, and here is negative. Okay, so this is strictly less than zero. Same thing for G3. Okay, but G1 of X star is exactly zero. Okay, now why do I say, why do we care about this? Because if you draw a very small ball around it, like here, you see that all the points in the neighborhood, how do you say this? In here. So all the points in the neighborhood satisfy the same situation. That so all points in a small enough ball are active only for G1. So what does that mean? It means that the one that you have to be careful about is G1, that you have to check boundary constraints. Okay, so the G2 and the G3 don't matter. You automatically satisfy them. So yeah. Okay. So if you have a question, tell me, because I need questions. It's very boring here. What's the question? Huh? Why not? I want to know. What is it? Yes. Yeah, exactly. That's the definition. Yeah. Good. Yes. You know, this is not YouTube. You can ask questions to like, yes. Good. But anyways, the point is that the active is a local property. Okay, so there's always a small enough ball by continuity of the G functions that you have active. All right. So we order the first constraints, G1 to GL prime, to be the active ones. And the remaining ones are called inactive. They're all strictly less than zero. Okay. So, and same thing as before, regular point is when the gradients of the constraints are linearly independent, which meant A1, V1, blah, 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 AN, VN is zero, implies that the coefficients are all zero. So you cannot have a linear combination of them, 2 to 4, or 2 to 3, actually. All right. All right, let's come back to this thing. So when you're, yeah, so when you study it locally, we can ignore the inactive ones. So let's go deeper into this. So again, you have your constraints, some of equality, some of inequality. So yeah. Okay, so how shall I say this? So yeah, again, the thing we said that active is a local property. So meaning that, i.e., because they don't explain it carefully. So if X star is active, there exists epsilon ball, so that all X in B epsilon X star are also active. Okay. So, and that's important because derivatives, when you are looking for local min, you only care about a neighborhood, right? So remember, local minimum means the register radius, so that the you have. Is that okay? Right? Remember, like for local min, you just need an epsilon, so that you have a local bump. Okay, so this is the G1 constraint. Your guy is at the boundary, and it has a local, let's say, bump. And there is a small enough epsilon so that all the points there have the same sort of property. Okay, that I shouldn't say it like this. This is confusing. So oh, let me say it this way, are also inactive for the same as X star. Okay, I just changed it a little bit, the wording, because you can see it from here. Some of them are inactive for G1, right? Like Y, G1 of Y is positive, G1 of Y prime is negative. But locally, they all have the same thing, namely, but G2 of Y and G3 of Y prime are both negative. Yes. Anyways, we'll talk about this more. I mean, they have to be feasible. Yeah, there's a lot of stuff here. We'll talk about it. It's fine.
So do you mean that inactive
If they're
is a local
feasible
property?
points, they have the same inactive constraints, but they have to be feasible. So it's better to draw the picture. So here's the picture again. This is G1. This was G3, I think, and this was G2. Right? Right? Hello? Okay. And anyways, I'm spending too much time on this. We'll talk about it. The point is, yes, so if they are feasible, so you're inside, they have the same issue with active, inactive, only mattering for G1. So locally, G1 is the only issue of being active or inactive. Okay. Is that okay, Daniel? Or whoever that was?
Yeah, that's
Hello?
that's good.
Yes. Who is it? Oh, Daniel.
It's
okay.
Daniel, yeah.
Yeah, okay. Yeah, we'll come back to this right now, actually. Yeah. All right, so again, yeah, so this is a very famous theorem called Karush Kuhn Tucker, or Kuhn Tucker, for the first order, and Karush Kuhn Tucker for both second order. And it gives you a local min for inequality constraints. Last time we did Lagrange multipliers. For equality constraints, now we give you the theorems for inequality constraints. So here's the theorem. You can find parameters lambda and mu j so that you have the first order condition over here, all 0. And For those of you who took linear programming, let me explain the second condition. It's called slackness. So let me do I know it's not a prerequisite, so let me just make it quick. So this is APM 236, something like that, linear programming. Okay, so you had the following issue, right? You had some minimize some problem, and you had given, AX equal, I don't know, B1, and then but you also had A2X less or equal than B2, right? You had like inequality constraints. And then you did the following thing, you introduced the slack variable. Remember? So you turned this guy into equality. So you wrote it as AX2 plus epsilon 2 equal to B2. And this guy here was called the slack variable. Okay? So you added one more variable in your system. And the analogous thing is this mu guy. So this mu guy is the slack variable from 236. Okay, because we want equality constraint. Good. All right. Yeah, so let me dig deep into this second condition. So what does it say? Let me remind you again, X naught is active for GJ if GJ X naught is 0, okay, and inactive otherwise. Okay, so that means that if it's inactive, you get from this condition, you get that mu J will be what? What does it imply? What? Yeah, it's 0. Perfect. Thank you. So the non-zero ones are only for inactive. No, sorry, so yeah, so when it's active, you have non-zeros, possibly non-zero. So that means the first order condition, which I will write in a second, is of the form J1 L prime mu J gradient of J X naught, where J1 to L prime are active. Okay, so that makes the first order condition cleaner. Okay, much easier to check. You just have to check the active ones at your candidate local minimum. We will do many examples, but that's the idea. So yeah, if GJX naught is not 0, namely inactive, then MJ is 0. All right. So again, I'm going to prove to you that local minimum implies these two conditions. So we've done this a couple of times. When there were no inequality constraints, we called it Lagrange multipliers. Okay, so think about this theorem as Lagrange multipliers, but for inequality constraints. Okay, good. All right. So yeah, we only care about the active ones. Yeah, X naught is a, so this is our assumption. X naught is a local min. So it's a local min only for the active constraints. Yeah, sure. Yes. So here's the active constraints. So I ignored the other ones. And this was the definition of a surface, okay? So this is how we define the surface as all the x that satisfy this. All right, some hyperdimensional surface. Yeah, anyhow, so from last week, this is last week. So Lagrange multipliers. These are the Lagrange multipliers. We have this condition, okay? So again, let me remind you, I'm applying the theorem of Lagrange multipliers to this case equaling because I know that G1 to GL prime are active, okay? Is that okay? I can't do it otherwise. I can only apply this theorem to the active ones because I need equality to apply Lagrange multipliers. I mean, that was the theorem in Lagrange. I needed to have equality. Okay, but we're going to extend this like right now. All right. So yeah, let me ask you this. If I show that in fact the Lagrange multipliers are non-negative, why would that give me the full thing with the inactive constraints? So let me write down what I'm asking. So we have this result, but it only goes up to active. I want to show the same thing. But for all of them. Why would non-negative give me this result? Just to see if you, yeah. Do I have the explanation right? No, because what is it? What did we say? We said that if it's inactive, then MJs are 0, right? So so yeah, let me explain it here. Yeah, whatever. So yes. Where is it? 0. Yeah, whatever. So what do I want? Yes, this summation. Right. Okay. So yeah. So if it's inactive, well, let me say active. If it's active, then J of x naught is 0, which means that the sum goes from L prime plus 1 to L of mu J Gj x naught equaling 0. But then if the mu j's are non-negative, then right from here you will get what do I want? Oh, but the point is also feasible, right? And I already know that Gj x naught is strictly negative. So from here I get Mj Gj x naught must all be 0. Okay, so how shall I explain this? So why do I need non-negative? Because if I already have the first terms are 0. And if I also show you no negative, then I get that the last guy, L prime L, will give me that Mj, at the boundary, whatever, Gj x naught will need to be 0. Yes. All right. And so you get the full thing. All right. Let's do the proof. Hopefully it will make sense as we work through it. Yeah, we already talked about this. All right. So again, we ignore inactive constraints. So we ignore inactive. Because mu j is 0 for inactive. Why? Because of mu j Gj x naught equaling 0. Okay. So now suppose that one of the mu j's is negative for the inactive. Okay. And it doesn't matter, we can prove it for j equal 1. It's the same proof. Again, this is our surface. They're all equal to 0, but we ignored G1. Okay, so G1 equaling x naught was removed. All right. So in a sense, it contains M, our other surface where we had it, right? Is that okay? All right. X naught, yes. So X naught regular meant that all your gradients were independent. So gradient H1, gradient HK, and same thing, G2, GL prime are Li. And remember, we had this trick that a tangent vector can be thought of as the guy who's normal to the gradients. Okay. Is that okay? And in other words, yeah, so I put it all together. the tangent space is defined as the complement of the span of the gradients, right? So that gives you the intuition of why it's equal to the linear combination, yeah, that we talked about. All right. Now, since these gradients are linearly independent, you have that this guy will not be in the span, right? This is from linear algebra. So because of Li, this constraint cannot be in the span. So in other words, the gradient of G1 will be in the complement of this restricted surface where we remove the G1 constraint. I will draw pictures on the intuition. I will do the symbol proof, then I will explain you what's happening. Let me just go through the motion. All right, so, but then, what is the definition of this? This is, so what is T, what is this? The definition of this are all the V's that are normal to the HIs and normal to the gradient GIs for I starting from 2, okay? But since this guy is not there, since it's not there, it will be non-zero, okay? So gradient of G1 with V will be non-zero. Can someone tell me why I can assume that it can be negative? So again, the definition of this set are all the V's that are normal to the gradients. Gradient of G1 is not in this set, okay? Right? So then can someone, which means that gradient of 1 V is not 0, but this is just a linear algebra trick. Why does this imply that there is some V tilde that it's less or equal than 0? It's a stupid trick.
Well, like if you have a V tilde, if you have like a V that's greater than 0, then you just take a minus of that.
Yes,
And then
very good. That's it. Okay. So if gradient of G1V is positive, take V tilde to be minus V. If it's negative, take them to be equal. Okay. Okay, I mean, I know this proof is very, I'll explain you why we care about this. So, all right, so far so good. So there exists such a vector. And now hopefully you remember a bit. Yes, so this condition, we called it first order condition. And it told you that this is a local maximum along that direction. Okay, is that okay? So meaning the picture is, I will draw many pictures. I will try to explain this more. So this is X naught. This is the direction of V. This is the graph of G1. Okay. And it says that if you move towards V, the function G1 decreases. Okay. The positive that we talked about is like this. So if some like minus V, no, let me say minus G1. Yeah, it will decrease. So it will go, yeah, so it will go up. I don't know, does that make sense? Okay, good. So this is you have this monotonicity. I will summarize the proof. For now, it's just step after step after step, because it's a very long proof, I know. All right, moreover, it's feasible All right, because anyways, yeah. So, and what else do I want to say? No, that's good. Yeah, so I have to explain this. So why is this a feasible direction? Um, so let's draw the picture again. This is G1 of X. We assume that GM1 of X naught is strictly negative. Okay, so you're inside and you draw a ball around it. Okay, and we just showed that the guy is a minimum along the V direction. So, meaning if you take G1 X naught minus epsilon V and G1 X naught plus epsilon V, these are both less than G1 of X naught, which is strictly less than 0. Is that okay? No? Because we just showed that gradient of G1 of X naught V is negative. So I should say, let me just write it this way. Let me write it this way. And then take epsilon to be this. Okay, so there exists a small enough ball that if you move in the direction of V, the function decreases. All right, good. That's all I wanted you to know. All right. I know this is a very long proof or a very important theorem, so I'm sorry, we have to do it. I mean, because you will see this, Karush KKT shows up all over the place. So, okay, let's do it carefully. Again, we have a definition for tangent space. The definition of tangent space was all the V, so that V is some vector x naught of some curve x of s belonging in the set M tilde. And the picture was, this is M tilde, and this is x naught, and it moves in direction V, and this curve is x of s. Is that okay? Let me make it bigger. All right, good. So I need this because I need to do mean value theorem. That's why. So whenever you see me doing this, I need to do mean value theorem. All right. So again, x naught by assumption was a local min. So locally, this differential curve will increase. So this is x naught, and this is xs. Function goes up. Yeah, sure. So this was our first order condition. Okay. And yeah, anyhow, so this is, we showed it before above, just by Lagrange multipliers. I will summarize the entire proof. I just want to go through all the steps. You take dot product of this crazy guy because we want to use our condition that this is non-negative. And again, let me remind you, the goal is to show that mu j's are non-negative. Right. Our V was in this tangent space, so all these guys are dead. So at the very end, you're left with this condition. This guy on the right, on the left is non-negative. This here came from the following. We assumed that mu1 is strictly negative, and we also assumed that we showed that this is a local min. Okay, so minus minus is positive, but then you also have another minus, so you get negative. And this is the contradiction. So the contradiction is that the guy over here is bigger or equal than 0, but this is strictly less than 0. So these two contradict each other. All right, now let me review the proof backwards, okay? Because, yeah, good. So let me review the proof backwards. So okay, actually, let me go to the beginning. Over here. And then we'll go turn this up. All right. I want to show you that if x naught is a local min, then you have this condition. Okay. Now, why do you care about this? Because when you're searching for local min, this is the stationary condition. Okay, you will have some minimization problem. I will do an example. You compute the gradients, you set them to 0, and this will give you a system of equations, right? Because these are vectors. And good. So this is what I'm trying to prove. When you're so the constraints that are active are very easy because you can just use locally, like I said, locally they're all equalities. So you can use Lagrange multipliers from last week. Okay, that's easy. The problem is, what if they're inactive? So you have less or equal. Lagrange multipliers doesn't work. Okay, so I cannot apply Lagrange multipliers. But if I prove you, so where is it? Yeah, anyhow. So if I prove you that all the MJs are non-negative, then I'm getting the full thing. Then I'm getting this guy is plus the call it star plus the L prime plus 1 to L mu J gradient of GJX naught is 0. Okay. What shall I say? Yeah, anyhow. So, but to do this, I need them to be all non-negative. Yes. Huh? Okay, yes. All right, so let's do this. How shall I do this? Maybe I should add only one extra constraint. So let me draw the picture again. Active, this is active. So like this is G1. Inactive means you're inside one of the other ones. So let me say like this. So we have G3 of X star is strictly less than 0, and G1 of X star is equal to 0. For active, Lagrange multipliers, I don't care. For inactive, yeah, so you are fully inside. All the points in here satisfy G3 being, negative. So locally, what do I want to say? Yeah, so for all x in a ball of b epsilon x star, you have G3 of x is also negative, okay? And from here, you do the same for the derivative. So what do I want to say? So let me do this here. X. And then what do I want to say? What do I want to tell you? So, what do I want to tell you? Confused. Yeah. Oh no, didn't we talk about this? Right. So if they are, yeah, you can ignore the inactive ones. Yes. So we talked about this. We said that the didn't I say that? I said that if GJ is inactive, inactive for X star, then it's inactive, like we said over here, for G for a neighborhood. And then we also said that this implies that the mu J's are 0 because we had like a product of them. But anyways, we said that we can ignore. So because of this, this implies that we can ignore them in minimization. Because all the ones in the neighborhood will satisfy it. So when you look for local mean, you don't care. Because they all satisfy the constraint. The problem happens with the active ones, where you could have some of the points in a neighborhood not being feasible. Okay, so you should think about this when we talked about interior points and boundary points. So here, if it's an inactive constraint, this is basically a boundary, an interior point for the inactive ones. Does that make any sense? How do I say this? I mean, okay, I don't know what to say. Like the lesson is from the discussion we had before, if they're inactive, we can ignore them. So we set mu J to be 0 for inactive. We set it. It's not a proof. It's like we can ignore it because locally they are all inactive. All the points satisfy G3 less or equal than 0. I don't know. Maybe with the examples, it will be a little bit better. Okay. Yeah, so if we also show, yeah, actually, this is your question. Not your question is not one, your question is two, because two implies one, because this will give you the mu j equaling 0. So let me explain why mu j non-negative gives you this, okay? All right. I mean, in a way, that's what we said. So, yeah, so because we can ignore it, because we ignore inactive, we pick our Lagrange multipliers mu L prime plus 1 to mu L to be 0. Okay, and for active, we need mu 1 to mu L prime to be non-negative. I mean, that was Lagrange multipliers, right? We needed our Lagrange multiplier guide to be what? Okay, we'll talk about this. We'll do examples. I don't know what to say. So let me finish with the review, then we'll take a break. Yes. So how do you show that the coefficients are non-negative? You assume that one of them is strictly negative, and then you remove it from the tangent space. So you have a space of constraints, and you remove the G1 guy. Yeah, and so you show that this constraint, this vector, gradient of G1, would be strictly negative. So we talked about this. Yeah, let me go backwards. Here. So, good. This is a gradient here. So we showed that this guy over here is negative. We have this is 0. This is a local min. I should have started with here because this is more clear. So then I wanted to use this condition to get that mu1 is forced to be non-negative. And but to do this, I needed a good V. So that was the whole point of the proof. Find a good V that will kill them. But leave gradient of G1 to be non-zero. Okay, so you should think about this is like a projection. In a way, we are projecting to the space of gradient of G1, and we're killing off the other coefficients, right? So if you remember from 2 to 4, when you want to show linear independence, you try to isolate the coefficient. So you have a question? Oh, yeah. So let me write it, clean this up. So want to show that mu1 is non-negative using 1. So I need a V that will isolate mu1 gradient of G1 dot V. Okay, and all that work was to use the following, that this guy will be non-negative by local min. This is easy. And then I just picked the V that will be normal to all these guys. That's basically the argument. All right. Let's take a break. Add more explanation. How do I explain it better? How does the book explain? What? Explain. I mean, you see how little I have to work with? Like, this is their proof. It's like 3 lines. And I had to do like 5 slides to like put all the details. Like, this is their explanation of why 36 holds. Like, let me see. What's a better way to... Oh. How do I say it better? How do you say they ignore? What's a better way to explain? Daniel, are you there?
Yeah, I'm there.
Yeah, what do you think of this active constrained? This was confusing, right?
Which part?
The one we just talked about.
Oh, look, the theorem proof.
Yeah.
Yeah, a bit confusing.
So is it okay that when the constraints are inactive, we can ignore them?
Yeah,
Does
that makes sense. Yeah.
because like, where's the picture? Because like if you take a ball around it, if X star is inactive, the guys around it will be inactive for the same guys, right?
Yeah.
Like G3 of X will be less than 0, G2 X will be less than 0, because this region here is the G2 less than 0. This region here is the G1 less, sorry, what is it? G3. Is that okay? So then that's why we set the MJs to be 0 for the inactive ones. Is that okay?
Yeah, that's also okay.
So where is the confusion?
I guess it makes sense then. So no more confusion.
Oh, come on, Daniel. Please help me.
At the last step, we said that we can find the direction such that the gradient of g1 dot v is less than 0.
Yes.
But in your final statement, the proof, doesn't that? I feel like the sign is wrong.
No, because we give a contra.
Like no, in number 15, I think statement 15.
So let me see. So we found a V where this is strictly less than 0.
Yes, and then we did the dot product.
And then but
so,
then
yeah,
but okay, like I mean here, right? So
yes.
this guy is negative, right?
Oh yeah, I forgot we assumed u1 is negative. My bad.
And then this guy is non-negative.
Yeah,
so
I just forgot that u1 was also negative.
yeah, but we can even, in a way, it comes from here. We're proving that mu1 needs to be okay. Anyways, whatever. Yeah. So this is negative. Negative is positive, but there's a minus, so you get negative, which is a contradiction. Yeah.
Okay. Yeah.
I don't know, like What else can we? I guess you will see in practice that the inactive ones don't matter. Yeah, all right. I don't know. Mm. Mm. Because like we're not asking for global min, we only ask for local min, and we are away from the boundary. Did it make any sense to you? No, it's just I'm not sure if people understood it, like that we can ignore the inactive constraints. Like remember the question you had that for interior versus boundary points. For interior points, you could just set the gradient to 0, and you're done. But for boundary points, you have to do this gradient being, along the feasible to be a non-negative. Like when you dot it with a, remember when you're at the boundary, you had like gradient of f dot v to be like this. But then for boundary points, right? But then when you're inside, you could just set it to 0, right? Well, because like remember when we studied the simplex, depending on what boundary you fall in, you have to check this condition. So this one only matters for the active ones, where you're at the but when you're inside, you just set it to 0. I need to find no, because you helped me with intuition. I want to find some good some as if okay, we'll see. Yes. Summarize what? But will that help you? But I mean, all the theorems there in the slides. Like I say, theorem, theorem, theorem. Or like lemmas. That's right, that's right, that's right. Yeah, we may have a review session, so we'll see. Yeah. But you only need to do the homeworks for the most part. I mean, yeah. Yeah, okay, let me start. I have to start. Okay. All right. All right. Okay, as promised, here's the where is it? Does it work? One. Yeah. So as promised, here's the sufficiency and necessary. So we will do examples. We just showed that if your guy is a local min, you need to have these two constraints. And the final one, as usual, is a convexity condition. So again, let me remind you, in the quiz, you had to find the stationary points, right? In a sense, these are called stationary points. But the point pi was not a local minimum. It was a saddle point, right? Remember? So you always need local convexity to get local minimum. And that's the condition. All right? So it's the same thing. Just because you showed something is stationary doesn't mean it's a local min. You need this guy to get local min. Right? Is that okay? So this one will give you all the candidates. This one will tell you who of the candidates are the criminals, the local mins. Yeah. So you put them, parade them. So good. All right. So we only need to prove part 3 because we already know they give you a local min gives you 1, 2. All right. So I need to prove you local min. All right. So I'm proving local min. X naught is local min. Given positive definite. Good. X naught satisfies the active constraints. Yeah, as usual. So that's what I was keep saying, that if they're inactive, you can ignore them because in a sense, you are an interior point with respect to them. So this is the G3 region, negative, and this is the G2 region, negative. So this is the G2 negative, and then this is the G3 negative. And this is a terrible, this is like, let me draw the better. So this whole region here is G2 negative. And this whole region here is G3 negative. Their intersection is over here. Okay? And if your local min is inactive for both, you can draw a ball that is in the interior of them. So you can ignore them because they won't give you boundary constraints. So if you remember, like in the simplex, if you're at the boundary, you have to check all these other conditions, right? You don't have to do this when you're inactive because you're fully inside. But not with respect to G1, because G1 hits it. For G1, you have to do Lagrange multipliers. Do you understand? So, yeah, anyways, I think that's the explanation. That's why we do Lagrange multipliers or the active constraints. And we ignore inactive because they are interior points. Okay, good. The more I say, the more confusing it becomes. So let me stop. Right, so this is our guy, and I'm going to show you that this guy is positive definite, semi-definite, with a, it could be 0. Because, yeah, any linear function is convex. Right. Right, so yeah, this is the Hessian. Anyways, we'll talk about it. So if you remember, all I need to show you is that this guy dotted with V from the tangent space would be non-zero. So Tx naught of M. So I have to find the tangent space, which we talked about. So I don't know. Okay, let me say it here. So remember from the result we had, we showed in the equality constraints, that this guy over here, L of x naught dot V, is non-negative, implies x naught is a local min. Okay, and but here M is the following surface H1. So I take, well, yeah, H1 is 0. All the HI are 0, and the GJ are 0 for J1 to L prime. Okay, does that make sense? So again, for people who took 236, it's the same idea, is that you had an inequality problem and you added the slack variable and you turned it into an equality problem. This is exactly what we did here. So we took the problem minimize f of x with h1 is 0, g1 less or equal than 0. We want to check x naught as a candidate, which one's inactive active. So g1 x star to gl prime x star is 0, but then gl prime they're all negative. And so step 3, we ignore the inactive ones. Ignore inactive because all x in B epsilon x star are same inactive. So they are interior points. So 4, we solve the following equality constraints problem. Minimum f of x, h1 is 0, and then also g1 to gl prime is 0, right? And this one we solved it last time with Lagrange multipliers. That's it. That's the intuition here. Okay. So now let's do examples to help you put some numbers to your head. All right. Minimize minus x, and here are the constraints. The unit circle and the line. So here's a picture. This is the unit circle. This is inside here you have G1 negative, and all the guys on the left of the line are G2 negative, right? So they only intersect in this half moon. Okay, this is the feasible set. Feasible. All right. And that's good. Gradient of f, gradient namely of minus x, is equal to minus 1, 0. So yeah, whatever. So minus of that. So the thing I wrote here would just be 1, 0, which points to this direction. Okay, because the vector 1, 0 is over here. So it points to it. All right. And then what do? Remember the local, what do I want here? Greatest decrease. So this is minimizer. Yes. So the minimizer will be the one whose tangent space, these are the tangent spaces, are normal to the gradient, right? This is normal. Right? So again, if you remember from 236, whoever took it, you slide your tangent space till you hit the set. So you move along the gradient till you hit the set, and this guy over here will be the minimizer. Okay? This dot, this is the minimizer. All right, and I'm going to prove that mathematically, but that's how you see it from the picture. You pick the first point where this tangent spaces touch the feasible set. Okay. All right, good. Yeah, so and this point would just be 1, 0. So let's check it. So I have to check the first order and second order. Also need regular points. So I'm just doing step by step, as you will have to do it in some of the questions in the homework. So to show regular, you need the gradients to be Li. Can someone tell me why they're Li? What's a quick way to check Li when you have two vectors? What's the fastest way? No? Do you remember? There's a quick way. Do you remember? You form a matrix. Huh? What? No, you don't need symmetric matrix. You just need to form a matrix with column vectors, the vectors, and you compute its determinant. And that's it. Okay? So please don't sit and do like solve systems and just put it, determinant, that's it. Okay, good, thank you. And sorry? Sure. So, I mean, what should I explain? Why are you asking me to prove why if determinant of A is not 0, then if and only if the V1 to Vn are Li? What? So one way I think is you do row echelon, and so yeah, so you start with V1 to Vn, and you keep doing row echelon till you get to some standard basis, and then yeah, anyway, so then they both have to have the same span. You can do it like that. How else to say it? Okay, fine. Yeah, so okay, this way is easy, yes. But I think he's asking about this way. This one is easy. You just do this, you just row echelon, and this will be non-zero. And then, but if it's not 0, yeah, it's invertible, but then you probably want to multiply by some standard vector. Something to isolate the V1. So like A of epsilon 1. Okay, what? How would you? Huh? Sure. I mean, but then we're talking about the same thing. Oh, yes, that's right. That's amazing. So do it by rank nullity. If you remember rank nullity, that's how I will do it. You have image of A plus kernel of A is equal to the full dimension. And because it's invertible, this guy is 0. Right? Any invertible map is surjective. Okay? Linear map. I didn't say any map. Linear. Anyway, so from here you get full rank, like you said. Okay, and that means your guys have to span the whole space, and there's n of them, so it has to be the whole thing. They have to be Li. All right? I don't know why I'm doing this. Who asked me this question? Like, you're never gonna be tested. Just come after and talk to me. Good. But yeah, it was fun. I spent so much time on it. Yeah. Okay. What are we doing? Yes, first order condition. So I have to check. I have to find you mu1 and mu2. so that this is 0, okay? All right, so I opened it up. Where is it? Here. I opened it up, and I think I gave you the numbers, right? Yeah, so you can put these two numbers, and it will give you a solution to this. All right, so you satisfy the first order constraint. Now I need to check the second. Okay, all right, good. Yeah, both constraints are active, blah, blah, blah. Yeah, this is easy. Okay, second order. So I have to check positive definite on the tangent space. So where is it? Over here. So this crazy, all these matrices, but it just turns out to be this. Is this positive definite? Why? Yeah, so eigenvalue 1 and 2 is 1 with multiplicity 2, and you're done. This was an easy question because you didn't even have to compute the tangent space, okay? Because it's always positive definite. But there are cases like I did last time where you could be negative definite, but not on the tangent space. This example shows that G2 can be active and mu2 is 0. So yeah, I should talk about that. So where is, yeah. So if you put G1 1 0, you get what? You get 1 minus 1, which is 0. But then if you put G2 1 0, you get you still get 1 minus 1. So what am I talking about? I have no idea. They're both negative 0. So they're both active. Yes. I don't know what I'm talking about. Oh, I see, I see. Yeah, yeah. So they're both active, yet it happened the Lagrange to be 0. Yeah, we never said that active implies non-zero. Yeah, that's a good point. Yeah. So just to remind you, inactive, Gj implies mu j is 0. Active, Gj just says that mu j can be non-zero. It doesn't say that it has to be strictly positive. Okay, good. That's all. It's a comment. Yeah. All right, let's do another example. Again, I will draw you some pictures to find you the candidate. Often we will just give you the candidate because this is too hard to do it yourself. So the question will be constraints, check that this guy is a local min. Okay. Or maybe I will put the picture just to torture you. I don't know. We'll see. Whatever you like. Anyway, so again, this is the gradient. Let me compute it for you. So gradient of f. Actually, you can tell me. I'm tired. What's the first component? Yeah. And second, same thing, right? No. What is the second? Yeah. Yeah, whatever. So I will give you the local min, and if you plug it in and do all the hard work, 4 plus 4 is 8 minus 2. 2 plus 4 is 6, so minus 4. Thank you. Yes. But if you take its minus, you get 2, 4, which is somewhere up here. So it points to it. Yeah, fine. And then how do you find the local min? You draw these lines, okay, normal to the guy. And the first time it hits it, you get the, what? Yeah, you get the local min. Yeah, anyhow. Okay, all right. Oh, that's an old, do we have a way to find the min? Yeah, so like I said, I will probably give you the local min because this is too hard. There's no way you can find it by even from the picture. It's impossible. So I will give you the local min. Yes. Yeah, I did this in MATLAB. I will put the code. So this is the 3D picture. How can you find the local min from this picture? This is crazy. Anyways, so just to explain, the f guy is that crazy function you just computed the gradient of, and these are the two constraints: g1 less or equal. Where is it? Over here. So this red curve, red surface is g1 0 and g2 0, and the negative stuff is everything above. So you get this little piece over there. All right. Yeah, I will give you the local min because it's too much. Okay, good. But suppose we give you the local min, now you have to check first and second order. So yeah, so this is your system, and yeah. So where is it? What do I want to say? Yeah, anyhow. So like you said, you gave me this. This is the gradient of f. This is the gradient of G1, and this is the gradient of G2, if you do it by hand, all right? And then I plugged in, and now I'm gonna plug in the point, 1, 2, on the very next one. Do I have to do, I'll do it. All right. Whatever, let's do it. But I will give you the local min, so you don't have to do this. This is if you don't know the local min. So in applications, you will not know the local min. So unfortunately, you have to do the following. You have to run through all the cases and check the constraints. So that's why I did this, because sometimes you don't know what the min is. So we're doing case 2. We're gonna find all the local minimizers that satisfy this condition, namely G1 of X star is 0 and G2 of X star is strictly less than 0. All right. Plus the first order condition. Okay. All right. G2 is inactive, so by definition, I set it to be 0 because I don't care about it. It's a neighborhood would be all the points would be interior points for G2 negative. So it's not a boundary point, so I can ignore it when I do Lagrange multipliers. So I only have to worry about the mu11. So going back, this is our system. And here I set this to be 0. Okay. So if you do this, you get the system. And then, yeah, I solved it here. So, okay, I mean, anyways, this is the whole system. What's a good way to, anyways, doesn't matter. So, so for a quiz question, I don't think you will have time to do this, but this is a good test question. So, namely, we will give you a system, and then you have to find the minimizers, the local min. We might give you some help, tell you which cases to ignore, because it can be a nightmare, I know. This, even just doing case 2 is disgusting. anyhow, so the point is, from here you get a candidate, and I have to check second order condition. So again, let me explain what happened. You have a minimization problem. Is that the one? I think so. Yeah. And the first order conditions, the first order conditions will give you the candidates. Okay. The problem is this system is very difficult to solve. Okay. So this system, once we write it out, is difficult because you have 2 equations and 4 unknowns. Okay, so sometimes you won't even have a solution. So that's why we have to split cases. So we split cases to make a star easier to solve. Okay. Good. So you do that. You go through one of the cases. Now you killed the mu2, so you have two equations. I'm looking. You have 3 unknowns, not 4. You solve the system and you get your local min. But then you still have to check that this local min candidate will be positive definite on the tangent space. So now let me find you the tangent space. Right, so this guy here is this. We can do this together, no? That's fine, whatever. So, yeah, anyways. So the guy over here, these 2 matrices, are these 2 matrices over here. Okay. And so I get this matrix, looks nice. And I have to show you that this matrix is positive definite. So do you remember a way to check positive definite for this matrix? We had a condition. Yes. So one of the leading minors is the A11, which is 6. And the second guy is the full guy, which is 36 minus 4, which is 32, which is strictly positive. Okay. All right. And yeah, so indeed, the 0.12 is a yeah, local minimum. But again, yeah, we were lucky. We didn't need to compute the tangent space, but we should do it because you might have to. So again, we ignored the G2. G2 is ignored because it's inactive. So you just have to study this space, namely all the guys, that are normal to the active constraint. Is that okay? So we are in case 2, where G2 is inactive and G1 is active. So we are doing Lagrange multipliers only for G1. All right, so let me give you the tangent space. So G1, let me remember. So G1 was the circle, wasn't it? Let's check. I want to do some computation. Yeah, so G1 is the circle of radius 5. Okay. So G1 was x squared. Wait. That was G1. Gradient of G1 is 2x 2y. And if you plug in 1, 2, you get 2, 4. Okay, so that's the guy. And I take the dot product. So I have 2v1 plus 4v2. And so, yeah, so you get the following system. You get 1, and then v1. So this guy is 1, and you get minus a half, right? Right, so this is the span of 1 minus 0.5. Okay, so it's a one-dimensional tangent space. Let's go back to the picture. Yeah. So what was it? 1 minus, so 1 minus a half. So it's like over here, right? And then this is the tangent space. Let's do it like this. So all these vectors over here will be, yeah, all right. What else? Right, yeah. So, and then, I mean, this was easy, but in the test, I will make sure the matrix is not positive definite in general, but only when you multiply by the tangent space, like here, you will get strictly positive. Is that a yes question? I have no idea, but it will be, yeah, it will be like this or homework, like. Oh, I see. Can I not make a contract yet? It won't be 3 by 3. So yeah, I mean, okay. If it's computational, it will be 2 by 2. I swear by, yeah. So, because you will not spend hours looking for positive definite with 3 by 3. It's a nightmare. So, computational questions, 2 by 2. Proof questions, like in the quiz, which was sort of proof, it will be multivariable. Yeah, but you won't have to put numbers, right? It will just be, yeah, good. And that's it. So 1, 2 is a local min because it's positive definite on the tangent space. Okay. Good. So where else? What's this? Oh, I see. Yeah, all right. So let me give you a even easier condition. So I want to talk about strongly active constraints. So again, let me remind you. If you get a problem with inequality constraints and we give you the local min, you will check which ones are active or inactive. If they're inactive, you throw them away. They don't exist. Forget about them. And you solve the, you check the conditions only for the active ones. Okay? All right. It turns out that you can even do better. You can even ignore some of the active ones and only check what is called strongly active. Okay? So let me explain what that means. So again, we order 1 to L prime. The active ones, inactive, do not exist because it's a local min. It's not global min. Yeah. Now, a constraint is called strongly active. If during your computations, you show us that mu j is strictly positive, okay? And so now we will, I think I will prove it probably next time. So remember, right, when you check positive definite, you have to check it on the tangent vectors, which were all these guys that are normal to the gradients. What we're saying here is you can even ignore some of the active ones and only check on the strongly active ones. Okay, so in other words, when checking that L is non-negative on Tx not M, ignore the following. So ignore inactive, you already know that, hopefully. And you can also ignore the active ones with mu j equals 0. That's all we're saying. Good. Okay. So we call it T double tilde. All right. Hopefully I have an example. Should I prove it now? This is a nightmare. How many? It was massive, wasn't it? We won't even have time. Can I do an example? Yeah, I'm definitely not doing this now. Okay, I shall do an example. And then it just keeps going. Jesus, this is a nightmare. You know what? Maybe I won't do that. We'll see. Okay. I think I want you having nightmares. All right, let's just do the example in like the half minute that we have. Same example as before, minus x with this G1, G2. We will give you the local min. This is too hard for you to find it, but it's easy for you to check it. So we will give you the local min. You have to check that it's a regular point. We did that before, namely that G1 and G2 are Li. You just have to check a determinant to do this. And I also found the mu1, mu2 by solving a system. And it happened that mu2 was 0. So now that means when you go and solve for positive definite, you don't have to look at the ones that are both this and this, right? You don't have to do this. This is a big, right? You can ignore this and just study this guy. Good. So who is that guy? This is just the guy who is normal to the G1. You solve it and you just get 2v2. You get 2v1 equals 0. So you killed the v1 guy. Yeah. I think I gave you the Lagrangian, but anyway, so yeah, it was this Lagrangian, which is always positive definite. In the test, it won't be. And you check only against these strongly active vectors, and you have this. Okay. All right. So I will deliberately put strongly active and active, so that the active will be harder. But if you know the result, it will take you half the time to do it with strongly active. Does that make sense? All right, good. We'll see. Okay, maybe not. We'll see. Whatever. Yeah. No, there's no dumb thing.
No, I just had to question.
Yeah.
So you know how you connect, did you connect the iPad to your laptop and then for you screen record, you
Like, well, I don't know. I mean, I bought it. Oh yeah, yes, no, but no, I've done it with a tablet as well, and but it's a nightmare because then unless you have a Bluetooth and you can send it to the thing. But what I did, one thing I did is I had OneNote on my tablet, and then I shared the link on my laptop. But that or but you have a tablet. I
Or
see.
my other option is that you can write notes and converting to PDF, sharing that and as I like writing on the solutions, everything.
Yeah, but even in the real world, people won't like that.
Won't?
Yeah, no.
I know it's boring.
Yeah, it's very boring because it's just you reading.
Yeah.
You know what? I will put some instructions.
Yeah. Can you-
Uh,
'cause I don't
so
know.
let me get this straight. You
'Cause I
have
wanted
a,
to write it as I go, like how you do it. But like, I don't know how to do it at the same time.
wait, have you tried just plugging it in and like?
You know, I've never like seen a crazy.
Oh, I know what my advisor does. Here's what he does. Very stupid. He has so you have Zoom on your tablet and Zoom on your laptop. Two different people.
Oh,
And the guy on the thing writes,
yeah,
and there's like you as well, right there.
but you're using the same link.
Yeah, like it's like a two people Zoom.
Oh, so. Oh.
I know it's stupid as heck. It only works for Zoom.
Oh,
I mean, yeah,
so it's like two different, okay, I get it.
yeah.
Some TAs do that.
Yes.
Like,
How many should I put? I don't know, like how many? What is a reasonable amount for 2 hours? I want to do 2 hours, right? What? I mean, I booked 3, but you will get killed if I do 3 hours. No, everything is online. Only the final exam is there. So how many? I don't know. You guys had midterms. How many questions do they put for a 2 hour exam?
Yeah, about that.
Right?
If there is like growth or
Okay, like which course? Like what about 237? What's a proof course? Well, maybe, yeah.
for
What about like 237? Did you guys take?
yeah.
So that's a window.
Oh, I see. But what about with the short and restricted? You said 5 questions, yeah. But did you, no, but can you give me an example of a course? Like you haven't done any restricted time yet?
No, but I think for like math courses,
Yeah.
like most of the math courses are like 24 hours.
No, I'm not gonna do.
Really?
No, 2 to 4, we had restricted time. What do you mean?
4.
Yeah, were you in 2 to 4?
Yeah, but it's a just 24 hours.
No, it wasn't.
Yeah, it's a,
I taught this like this semester.
oh, I did like that.
Yeah, last year everybody was dying. I mean, like we're talking about now, like yeah, okay, 5 questions. Let's do. But it doesn't matter because I can still kill you with 5 questions. I mean,
Yeah,
it's not
so
really.
exactly.
Who cares? The point is just do the homework. I mean, right? Like the quiz, people who did the, one part like, and make sure you read the feedback of it. Yeah, because we were scheming for people to use the feedback to make questions out of the feedback. Wait, what? Oh, there has to be at least one because it's in the quiz. No, you will have a 2 by 2 matrix for sure. What's variable? Wait. What was your question? But then it will have multiple parts.
Yo, I don't like multiple parts.
Oh, actually, yeah. Do you guys prefer one topic with many parts? Like, how do you gain more? Because, oh, I see, because you can lose marks like that, right? Because they carry over. Oh, I see. No, but let's say you have like a second order, right? And you made a mistake with the gradient, then
Yeah,
it
that-
carries
okay.
over to the second, right?
But I believe if you.
Well, yeah, because you made a mistake. I mean, like the misunderstanding carried over for you, right? I mean, it was like, so more questions, fewer parts. Then. Yeah. I don't know. You guys can tell me. I don't care. Are we not generous right now? No, now they're free. Like I listened. I put it on free. I don't know. And he told me, should I do 2 hours free? And I said no. And then he put some feedback, and I will test you on the feedback. Because it's